Okay. Hello? I'm audible? Okay. Then welcome to my seminar, the Sorbus Computer, or how I built my very own 8-bit computer. This all started when I was preparing a talk that was also given here last year about the history of the first home computers. So while preparing the talk, I had the idea, wait a minute, wouldn't it be nice if there would be some hardware I could hand out to people so that they can tinker around like with the first home computers? So that would be a rather nice thing to do. And also during this preparation, I read about how the Raspberry Pi Pico was used in a lot of retro gadgets. So for example, in the C64, you can use it as a SID replacement. Another guy used it to replace some expensive RAM chips. Was cheaper than with the Pico. And I came about, Also during this came up something that Eben Upton said, that you really can use the Raspberry Pi Pico with 5 volts on the GPIO lines with some exceptions there. And then I was thinking about, okay, we've got this CPU, we've got this add-on with a computer in the middle. So how if we just eliminate the computer and only have the C64 and the Pico, and then, well, I tried that. So my ideas about this computer was, it had to be more than a toy, than a full-featured computer. It had to be, at least in the first state, done very quick, so I only had 2 months from the idea to having something that could be presented. And for me it was to learn about the 6502 processor family in total, not just the NMOS one, but also all the other ones. So the CPU should be shown in action. And of course, since I only got two months, it needs to be simple, stupid. It should be open, so open source, open hardware, it should be expandable, all that stuff. And the first ideas that I had was that it should be just 15 euro to run like an old computer, and then to have a diagnostic monitor where you could see, like with a signal analyzer, how this CPU was behaving. And the idea is, so as a toy, it needs to be really cheap. So my basic idea was 10 euros. Then I soon realized the way I wanted to do it, it can only be done something like 15, and after that it's been going back and forth ever on, and we'll get to this a bit later on. So I was taking then, if I want to use the 6502 processor, I was then taking a look at the pinout and realized there are 38 pins, plus ground, plus volt, makes a total of 40. So, but for GPIO, there are only 38. That's the interface. And not all are required. You see there's something like is non-connected. There's another one like the phi 10, the phi 20. These are just clock signals put out again if you want to add something else. It is even in the documentation specified that those shouldn't be used anymore. So there are a lot of things that could be stopped on. I realized the sweet spot would be 31 pins. With a compromise, dropping sync, it would be 30. 30 sync is a thing that shows that a new opcode is being processed. So we also get to that one bit later on. Why 30? Because the Raspberry Pi Pico only has 26 GPIO pins. So, however, the microcontroller that's on there, if you take a look at the specification of the data sheet, then it's stated the processor has 30 GPIO pins. 4 are held back for Wi-Fi, the LED, and also power regulation. The system itself is a dual-core M0+ architecture, which runs unoverclocked at 133 megahertz, which is the default stated. It can run overclocked for even something like 300 megahertz. Only this, then you don't have access to the flash anymore, so up to the flash it's 240. That's a rough number. And of course, somebody like my friend Ali from AliExpress built some boards that utilize all those GPIO pins. And the fun part about this is also 60 megabytes of flash, not just 2. So we can do more stuff with it. And, which is for me very nice to use, it has a Type-C connector. So, my idea on how connecting all these together would be like using a very old computer. So this is the Southwest Technical Products Corporation 6800. So it was utilizing Motorola 6800, and it was from the mid-70s. And everything you see, there's a backplane that is passive, and every active component is something like a card that's being dropped in there. So if I'm exposing the bus, then I could every component create as a card. So I've got my passive backplane. It is possible to use this one then for, of course, the 2 cards and also some add-on cards that I might be creating later. Then I've got the card that has been using the CPU. So it is really just the CPU. I just pull up a few pull-up resistors to make sure that the will work stable, that the processor will work stable. Then we've got the microcontroller, which I declared as the chipset. This does all the rest. It provides RAM, UART. It provides also generates the clock signal. So it's running about now 1.15 megahertz without overclocking. And I put it all together and just call it a computer. So I've got one specimen of this version with me. I want to hand it over for you. Just hand it through. But of course, as we know from history, it didn't stop there. So computers got optimized, they got more integrated. And also having the people solder all the joints, something like that, we came up with the idea on putting it all on one board, because there was never really the intent to switch everything out. And this makes then the price going about 10 euros. And it's then less solder work. Also, if you want to have it as a project with kids or so, it's very nice. And also, shout out, the first person who saw this would be the good idea and done is the late Streethuff. A computer needs a name. So I came up with a name with no surprise of Sorbus. Sorbus, the German term Vogelbeere. I picked this one because mother always told me don't eat those. So don't use them for the primary purpose. But playing as a kid with them, I had a lot of fun, and I thought, this fits. The first idea I had for the name was Lemon, because if life gives you lemons, makes a computer out of it. But Lemon already was an Apple II clone. So my first step then was to replicate a known computer. And the simplest computer I can think of with a 6502 processor is the Apple I. It is just a chip that has 2 8-bit GPIOs, one for input, one for output, and half of the PCB is only the circuitry that generates the video. So it's a very, very simple machine. And this part with that generates the video will be done just by a terminal via USB. So this is already something that I can drop. And I really just have to implement, I've got the CPU, so I need to implement RAM, ROM, and this bit of I/O. Once the Apple I clone was running, I wanted to have this system for teaching and learning. And of course, since it is so hard monitoring the 6502, I decided that I want to have it called a reference to the Tron, to the master control program. But of course, it should be that obvious, so I renamed it then to monitor command prompt so that the initials still working. So we've got our mini monitor for software for doing a bit of things or more to looking at the machine. So typically you compile the code in there. And if you want to see things, the default clock is running at 5 Hertz, so you can really see what's happening through each clock cycle. But of course, once this was done, as the first goal, so after the first 2 months, then ideas came up. We need to build our own computer on top of that. So I then came up with some own design, Similar, so I've already taken a look at Apple I, Apple II, Commodore line, VIC-20, C64 and stuff like that, so I knew all those stuff, and I was thinking, okay, let's do a boiled down version of the simplest thing from that one, and this is, so. I did a setup of the architecture of the microcontroller, or I used the dual core architecture of the microcontroller, so I had one core that will do the console stuff, all this UART, all the input, and the other core will then handling the bus in a tight loop. And it also is doing a lot of internal stuff, so handling something like a GPIO or so. This is done also, and I might be changing some of logic, trying to move this one out from this bus core to the console core, but I'm not sure about that. It still has to be as stable as it is before, and there is a lot of things. But the interesting question there is, why would I want to do that? Well, the clock is a bit, let's call it, uneven. So if we take a look at the signal shot with a scope, typically this should be really an even rectangle. So low should be as long as the high, and everything should be the same size. So as you can see, low is way shorter than the high one, and I've got even longer high one because some C code is executed there that is more complicated than just fetching something from RAM or ROM. The memory map of the machine borrowed a lot of ideas from other things, trying to keep it as simple as possible. Since I've got enough RAM within the microcontroller to do the RAM, everything not defined otherwise is used as RAM. Then from the C64, I took the idea of everything in the D bank, so D0 to DFFF, would be reserved for I/O stuff. And after that, there is some ROM. The ROM is banked, but it also has a RAM bank like the C64. And the last 256 byte is the BIOS, which is the same on every ROM bank. So this implements, for example, the switching between the ROMs, or between ROM banks. As of 2023, at the end of the year when I started working on this project, the software was still quite sophisticated, but at least the basic things were there. We've got a WASMO imported from the Apple I. I also always wanted to know how the terminal interface monitor, so the chip that was sold together with the first 6502 CPUs, which had some ROM, a bit of RAM in there. You just needed another RAM chip, the CPU, clock, and then you had your full self-built computer. And I wanted to know how it feels like to use this computer. Spoiler, it's not that fun, but you get your job done if you need to. And also there was some crazy Scotsman by the name of David Given, who has ported CP/M to the 6502. Why? Well, because he can, and he already did his own re-implementation on the 8080 as well. So once I had this, CP/M requires some kind of mass storage, so I needed to implement mass storage. And since we already have the file system from CP/M, then the kernel got added with a file system routine so they could load, save, also from outside of CP/M. So most kernel functions are provided via software interrupt. We get to that a bit later on. And building 6502 code is also done within the same project, so you just can download the source code for the whole project and build everything in there that contains the ROM files, the firmware for the microcontroller and stuff like that. So it's rather simple at this point. So this is a short overview of just a subset of what's provided in ROM, but quite interesting for me is that only the most basic functions, reading a char, writing a char, having a short print routine, those are implemented within the jump table like it's known from the Apple, from the Commodore machines. Everything else will be executed via the software interrupt. So the software interrupt typically is break with an operand, which never got implemented in any way, and I started, okay, then I'll be the first. And at least as far as I can tell, I haven't knowledge of everything. But I've done my breakcode, and the opcode then tells you if you want to do a file system load, file system save, something like that. And we've got a lot of special things that's in there. So one thing that I also already implemented to have something for the size-optimized code guys, already a sign table generator in there. So it's just 8 bytes to generate a sign table. And then we got a lot of other software added within the year of 2024. So, of course, if you have got something like an old computer, you want to have something like an old BASIC there. At least I want to have it because when people are coming in, you're doing an old computer, can it run BASIC? Yes, it can. I've ported the only BASIC that I've seen that runs within 8 kilobytes of ROM, which is the Microsoft BASIC 1.0. So even the C64 and VIC-20 had 2.0 already. There's Tali-Forth ported. There is support for the CC65, so this is a C compiler for that machine. And also, what's quite interesting for me, what then got added rather till the end of 2024, I've now included my own machine language monitor. So I can also do assembly code on the machine, which is very, very helpful. And so most of the routines were written by myself, but the code for assembling and disassembling, this was a code donation given to me by Apple. Well, unwillingly, because I just ripped it out of the Apple IIc ROM. But this is what everybody else did back in the time without crediting them. So, and also, since this machine runs on a 65 CO2 processor at least, you need, when you insert a 6502 NMOS version, then some, let's call it emergency system monitor, will then be loaded and run. So with every CPU, you can use the machine at least for something, most probably to figure out what's about the CPU. But then we also realized we had this wonderful thing that you had this with the MCP, with this meta machine, that you can look onto it. So it was implemented that when you press Control and square bracket closed, the CPU is halted, and then you get to some kind of meta system where you have a fully implementation of the system within C on the microcontroller, where you can go for everything, take a look, disassemble code there. And you can also trigger this meta mode in software by writing to this address. And the cool part about this is, with here we can really see what's happening. So if you want to jump to a subroutine, we can see the opcode is 20, the low byte is 0. Then we see that it's working with the stack. Then we see that the high byte is read. Then you can see that the address has then jumped to what we had here. So, and you can really then, like I would then shake the hand to every cycle, clock cycle that's running. But I'm here the venue for a demo party. So then the question is, how are we going to make a demo machine out of it? Because an ASCII terminal isn't that fun. Then there came up the idea of doing some graphics. First design choice was to use VGA or DVI. And even so, I've already been given getting some questions about this. Why didn't use DVI, HDMI? I feel that VGA is more fitting for 2 reasons. First of all, really analog stuff. Also, it's easier to implement. So if you want to run a VGA signal, you can use the microcontroller without overclocking. For HDMI output, you need to overclock it to get a signal that can be used by a display. But if we take a look, the RGB, we already need 17 of the 30 GPIOs. Just for displaying the video signal. So we need at least the data bus, which are 8 bits, so we are at 25. Then we've got the read-write line, the clock line, the chip select we need, so we need the we have got the interrupt and the reset, like we had on the bus available. So again, total of 33 bytes. So, and even no address, we only would have really just one way to select the chip. Well, what we can do is we don't really need the reset and the IRQ. So we've got now 29, and we've got even one to spare, which will be coming in handy. And instead of now writing to separate registers, think of it as you are giving out your commands on how to display data, like over a serial line. And this is an idea that I had driving back from Evoke on 2023. So that was then the idea, okay, we need to come out. So this is the only way that I can give out enough commands. And this led to the question how we make a simple chip select. So the chip select, then, we need to figure out some way to do this. Of course, having started my demo scene career on a 2600, I already instantly thought, okay, that needs to be in the 0 page. And even easier, to make things easier, let's start it at address 0. With our spare one that we have, we got the addresses 0 and 1 for address decoding. And to do this, the hardware is either an OR or a NOR gate. It doesn't really matter, because what we can do there is, since we are using the software, we can decide ourselves if we want to have it low active or high active. So, okay, now that this has been solved, how we're going to get an OR gate with 15 inputs? One of the things we could do, we could use a custom I/O chip that's programmable, so a GAL or a PAL. But this is too expensive from my point of view, since I want to have a cheap machine, and it's also hard to reproduce since you need the programmer. You could use a cascade of 4-bit, 8-bit inputs or NOR chips, so something like 74 series chips. But those also make this machine expensive. So I've got the idea of using a hardware hack like this. I just use diodes. So if anything, one of those lines is high, the chip select line is pulled low, and if something goes high, then it's not chip selected anymore. So, and this goes for all the lines, so if just one line goes up, it's clear that the chip isn't selected. And that idea I already came up with when I invented the hardware for the official Boulder Dash for the VIC-20, which is a limited edition of 8, available at Paisel Uli. So storm his Forum 64 account. Okay, and of course, I'm reusing the same microcontroller board again to keep things simple. The hardware is already done. The output works with the VGA examples by the Raspberry Pi Foundation, but the whole firmware needs to be defined. Also, what I want to get in there is USB keyboard support. There already is a similar project that uses Raspberry Pi Pico to implement really a full terminal via UART and USB keyboard input, VGA output. And this is something that I'm trying to use as a basis, so that I have at least a self-hosted console already and see how things are going from there. But if you want to define your own graphics card, this might be the chance to do it. So I'm also handing this one over. And we need sound. This was a rather easy thing to do since I learned about the ZKick Pico project, and I said, okay, let's just use that project and adapt the way that it's talking to the bus slightly so that it fits to my design. And again, how to do the chip select for this, since it is done different. You've got a chip select line on the C64 for the ZIT. So I've again used my poor man's OR gate, and I inverted everything so I have a poor man's AND gate. And in this case already, I needed just 2 chip select lines, and I have to check them both, and this then will work. At least I hope so. But why stop at a ZIT? How about a mod player? Well, then we need to load the mods from somewhere because we only got, as a flash storage hardware or internal drive, something like 4 megabytes. So it is not good for a ZIT collection. So we need to add an SD card reader. There were a few GPIOs spare. But again, after I added everything, I came up to 31 GPIOs. The running gag of this project so far. And also what we then can do is, instead of reflashing with a different firmware so that we have either mod support or ZIT support, this is right now the case. We have, the idea is to have a special I/O register that then will be able, so that you can select what it's going to be. If you want to have an SD card interface so that you can load something from a FAT file system, similar to something like an SD to IEC or so. You can have then a ZIT emulation, you can have a mod emulation. And already I had a discussion that, of course, there's a POKI emulation missing. So if you want to add this one, I give you all the hints that you need. Let's talk about this. So, this is what then the soundboard works, which I'm handing over. But at late 2024, I got a crazy idea. At least I thought so. There is this website that I like to tinker around with, 6502asm.com, which is now defunct. You can think of it as most probably the very first fantasy 6502 platform. So it's a computer that's just using a bit of memory for a frame buffer. Each byte written to this frame buffer is displayed as a C64 color. And this is implemented in JavaScript. It also has the assembler. I only need the runtime environment. But the downsides of this implementation are that since it's a JavaScript implementation, it's rather slow. And since it's slow, it doesn't need to do any syncing. And the addressing of the frame buffer, which starts at 0200, which is a bit strange since it's not on a boundary, on a 1K boundary for a 1K frame buffer. I thought, okay, that is something that I also need to change. So I can't do really something like a hardware implementation of this one-to-one, but I can use all the concepts and then come up with something that is very familiar to that or similar. Which then will look something like this. Of course, I need to switch back. So, I'm just using, yeah, it's running. Those typical NeoPixels, as they are called, so the WS2812 LEDs. With this, I've got more colors. And I've also got the problem that those are taking, a single one doesn't take a lot of power. It's, if you do a bright white, it's something like 40 milliamps. But if you have 1,000 of this, it's 40 amps. Multiplied by 5 volts makes it 200 watts. So from a former project I noticed that having bright white is something like, I would call it eye cancer. If you look at it, you're really blinded. So I knew, okay, half is enough, and most probably I wouldn't have all white for a long time anyway, so it should work even with a 90 watt power supply, which was the best price per performance I could get for this. But there were also some changes I needed to make. The frame buffer is at a different position, and the LEDs now update via trigger. So I've got a control register, frame buffer has been updated, please display. And with this concept, I get something like up to 30 frames per second. But I've got adaptive sync included for free. Yeah. The downside is, of course, the software must be ported. But I already did it for a couple of things, and also it makes more sense to write something new for it than just to watch the old stuff. So, Then I came up with a question, how to connect this one. I just repurposed one of my old chipset boards, and I took up the 4 pins that I don't need, that are required to drive the CPU. I don't need to drive the CPU, so I can use this one. I desoldered this one, put another header on it that sticks out, and then I can connect the LEDs in there. And I can even decide if I want to have one line for all 24, or even split it up. So I would even get a faster performance, but doing it all over one line was the easiest to wire, and you can see it works quite fine. So once it worked, then feature creep set in. And I was sitting there and wondering, okay, so since I'm just monitoring all write requests for my frame buffer, shadowing this, I've got enough RAM. Why don't do I do a shadow of everything? Shadow the whole RAM. So, and then I can also have some more commands, so I can state, I don't want to have the full frame buffer, just a part of it. And I can have some stepping, so I can move over a wider range in memory. So have a picture in there and then just move over it just by setting a new start address. So there are a lot of ideas to set in, and then something like a versatile DMA engine was defined. I wanted to call it Blitter, but I was then explained that a Blitter does a bit more than just a DMA engine, so I fell back to DMA engine. Yeah, and also for a subset I had, also I can add transparency then. So this is what is done with a font. This is just copied over as in transparency. But once I did this, I had then this interesting question of, wait a minute, if I have this fully configurable from the software side, then somebody can just state the frame buffer starts at the last address in memory, and then copy something from there to the screen. So this would be typically out-of-bound access, a normal program under Windows, Linux, something like that would crash. Or it would be a security leak, something like that. And I was sitting there wondering, okay, how can I prevent it? What can I do to get things done? And then I figured out, wait a minute, if I've got 64K of RAM, I can have a bit more. I can have 72K of RAM, which is the maximum then there. So if somebody tries to access behind it, it just gets the initialized memory. Also for writing to the frame buffer, it just writes into space that is never used. So problem solved, and no performance hits by adding something like a different if statement or so. So the architecture there is also quite elegant from my point of view. So we have got a bus sniffer, which is then implemented using the PIO engine, which is a specialized assembler just to handling I/O stuff, and that runs outside of those 2 cores. There are 2 engines that can run 4 threads each, and I'm just using 1 engine with 1 thread, and this makes it very convenient to wait for the write access and then get this data. Then I've got my what I call quick bus evaluator. So just checking if it's something that I need to cache or if it's a control register. The control register gets written through the multi-core FIFO pipe, through the main worker, which is running on the other core, and that handles everything, the copying from data to the frame buffer, and also sending out the LEDs, color palette changes, anything. So this is what this PO code looks like. It's really rather simple. So our GPIO 24 is the read-write line. So we just wait, then it gets 0, which is then the write signal. Then we just wait. We have seen the clock cycle. The most stuff happens on when the clock cycle is high, so we wait for this. And also, since things need to be settled after this, we also wait 2 more clock cycles of those PO. I'm awake now. I'm awake now. Okay, do we have sound again, or is it blown? Okay, okay. No problem. Okay. Okay. And then after all those premises are fulfilled, then I can just read the 24 bits of the address bus and the data bus. Then those will be written to a FIFO that then will be picked up by the C code. And then again, I just wait for the clock cycle to go low. And with rep, we go back to rep target, and it starts all over again. So it's really that simple to come up with something like that. And another thing I wanted to share about this thing, about lessons learned, is a question now for the C experts in here. Where do those two statements differ? What's the difference? Any guess? Yeah. Hand him the mic, or have you dropped it again?
So if the address is a signed value, it won't work.
No, this isn't it.
It's yeah, I thought this too, but it's unsigned 16, so that's not the point then.
No, it's all unsigned in there. So let's discuss. One A, second guess. Mike? No, okay. The interesting question is about the. Let's think about the ARM CPU. On the ARM microcontroller, the second statement is significantly faster because when you have to store 16-bit values, they will be stored already in memory. And if you have them as an 8-bit value, which although the shifting is with 8-bit, they are then handled within bits of the command itself. So this gives me a speed boost. Just with two statements like this, give me a speed boost of 7.5%. So I thought this might be worth sharing if somebody does coding on microcontrollers, maybe for demos, to optimize the code. Because I was really surprised, I was assuming that the compiler would optimize this on itself, but it doesn't. Yeah?
On? Oh, it's on, okay. What's the native size on that platform? Because if it's
You went 32. Oh, it's 32-bit.
Don't all of these get like promoted to 32-bit anyway?
Not with the way that I did it there. So I'm just figuring about those 8 bits, and those 8 bits are part of this instruction. So there are some bits left over so that you could put it in there. But about the details, we can discuss it at the end. Another question?
I think I know what he meant. He meant on the C side that the default int is of size 32.
Yeah. So the microcontroller runs with 32 bits. But however, if you have got only a subset of something like 8 bits, then you can mask it out by really going for 8-bit values because those values are included in the instruction.
Okay, and that is optimized by the compiler.
This isn't optimized by the compiler if you go for the first term.
Yeah, okay, but for the second it does.
For the second it does. Okay, so I was talking about how cheap this thing is. Let's take just a short look at the prices. So as you can see by the parts, building the updated version, the junior, which I forgot to hand over. Let's just do it now. Is 15 euros in parts. And the big problem about this is that the CPU is about something like 10 euros on its own. The soundboard is 7 euros in parts. Also, I can't really tell the exact prices for those, so I chose a number that will then round up the total sum nicely. I had this in my parts when I bought them, when I started the project, and I never took book about how much I paid. So for the VGA card, since there are significantly more parts of my parts bin, I decided to put some from there as well. But still, it's something like 7 to 8 euros. So in total, this whole platform with baseboard, graphics, and sound will be something like 30 euros. And I think for something to tinker around and also to learn new stuff, it is quite interesting. Well, let me get back a bit. And for the board, I've had 4 16 by 16 panels that I just concatenated. 26 euros. The power supply, because this was the sweet spot of the price, for something like 200, it would have been 50 euros or so. And a big shout out to my father who built all the woodwork of this stuff. So thank you for that. So now as a final part, this is the main contributor to the price is the CPU. When I started, the price was €2.50. Now I paid 10 euros or over 10 euros for one CPU. So why? Well, the first batch that I could use, they were refurbished. But the last batch, for something like half a year, I've been now scouting around AliExpress and eBay, and every single 65 CO2 CPU I bought from there are fake. They are, as far as I can tell, desoldered from some working machines or from some machines that they got. They didn't have even to be working. They were then just the original marking removed and a new one printed on top. So I got a full mixed of bag of everything almost in there. So every brand was involved. So at one point I had the nice idea, okay, let's go for the SCO2 because every faker goes for the CO2. That didn't work out either after a short time. And it's even done the other way around. I've got one 65 SCO2 which was rebranded as an NMOS one, but I've got NMOS now something like double-digit working ones that I really don't need because with my project they are not really that good to use. So if you need to fix something like a VIC-20 or a 1541, let me know, then I can dig through my parts bin there and see what I can find for you. But this led to one hidden gem within this thing. There is another machine inside the machine that I implemented. This machine is for detecting the variant of the 6502. So instead of just trying to run some code on the gem, on this native machine that I built there, or to do something like within the MCP and take a look there, I decided really to develop a new machine. And it really just needs to be as simple as it can get. We just need a bit of memory that needs to be executed. And when writing at a specific address, this is the return value that I can then fetch and have then the output there and know what kind of machine this is. And why I did it, it's an easy way to detect those fake CPUs, and it was an awful lot of fun. Also, I realized later on there were some persons doing it better than me, so the CC65 can detect the CPU in software, while I can only detect 6, they can detect over 10, but those are not pin compatible, so it doesn't matter to me. And mine is way shorter. This is what the flow chart looks like. So due to the how far we've gotten already within time, I suggest we can get over this one in detail at my place, if you really want to know about this. The green ones are just the things that I'm actually doing. The blue squares are showing how the CPU behaves differently. The red ones show the exit on what it is, and the yellow ones are then really how I detect the differences and then how the code branches out to the different machines. So, and to come up with this thing was really big fun. There is a very long document within the document section of the project, which is, I forgot to add the URL, I just remember. On GitHub, just look for Sorbus Computer, you will find it. And there is something like really a lengthy essay written on how I came up with the idea, how all the different machines behave and stuff like that. It even detects the very first ref-A CPU, which is one opcode missing, the raw instruction. If you got one, so that I can prove right that my machine works, please let me know. So, and these are all the topics that I couldn't squeeze in within this talk, since I've been working on this for 2 years now. One of the most interesting things that I've got with this is I've got hold of the 65CE02 processor, which was the successor that Commodore Semiconductor Group invented and had used the same core within a different chip within the Commodore 65. So there's a lot optimized. There are no clock cycles that do, these are dummy calls. They all have been removed. So that's a quite interesting CPU to take a look at. I also got one with me so we can take a look at this. This is just one of the things, break for kernel calling. If you want to know how I did this, what the upsides, these are advantages, downsides, what they are, let me know. Come visit me on my place. You will recognize me then by the LEDs. I will have them put up. And yeah, that's it. I wanted to show the system running, but since we only got 5 minutes left, I suggest that we go to Q&A. Since there already is a question. And the demonstration will be then at my desk.
I wanted to ask about the jitter in the clock. Have you thought about using the second PIO engine to generate the clock?
I could even use a timer for that, but in this case, then the C code would have to follow the clock, and that would make the system significantly slower. Because right now, the C code is running as fast as it can. Then it has to wait at one point or another for the clock to come up. So instead of something like having 2 megahertz, or 1.5 megahertz, 1.15 megahertz, it would be then something like 50, half a megahertz or something like that. And I think that's, and the CPU works. The whole system is working.
Okay, and what if you were to add other hardware, like, for example, make an expansion board with a real SID that requires correct clock?
With the real SID, it just won't work because this is snooping on the clock cycle to do the stuff. You can even figure that out if you change the timing routines back to what they were before. It was changed to a timer, so you could then hear how awful it sounds then. Also for the sound, which I forgot to mention, it was on the slide, Soundcore, the whole sound stuff was, the software was mainly done by Benson of TRSI, so I'll thank you for that. Okay, so I think that's it. If there aren't any more questions, then I can just finish right on time. Oh, there's a question. So I can't finish right on time.
Yeah, thanks. First of all, thanks for the entertaining talk. Quite impressive work, and it was very interesting to see the progress you made in the course of the project. What is the resulting frequency of the CPU? Maybe I missed that.
So the microcontroller is run with 133 megahertz, which results to a clock speed for the 6502, which is 1.15 megahertz roughly. Because it's jittering, you can tell if you're doing only RAM access, it's more than 1.25. Okay. Thanks.